Hi, my name is Sidharth. I'm a master's student at Stanford in the Space Rendezvous Lab, and today I'm going to be presenting on a Gaussian splatting-based guidance strategy for shape reconstruction of unknown space objects. There are demonstrated cases in literature and practice for rendezvous proximity operations in a known and cooperative environment. In this case, the shape and pose estimates is known and shared between the servicer, our spacecraft, and the target, the spacecraft of interest that defines a relative orbit. What we want to look at is what would happen if we did not have a cooperative system in which the shape is unknown. Examples of this include spy satellites, where we want to try to survey them and understand what they're doing for national security purposes, or on the space sustainability side, where if you want to remove space debris, you have to first characterize its shape to do a safe RPOD operation. And so the key question that our research answers or looks into is how do we do shape reconstruction of an unknown spacecraft? To start, existing literature has investigated 3D shape reconstruction. Existing visual methods include SLAM and point clouds, but they create sparse models that are sensitive to changing illumination and are only proxies for reconstructing the visual shape estimate. There are other image-based methods that learn the scene, albeit through computationally expensive models, such as neural radiance fields NeRF and 3D-GS, 3D Gaussian splatting. These methods can learn the shape of unknown spacecraft, but follow a prescribed inspection trajectory. And so the images they collect for training are always from the same viewpoints. Other work builds on this through active view selection. Some methods for spacecraft guidance change orbit by optimizing geometric proxies like surface coverage or landmark uncertainty of point clouds in a model. But point clouds are not a representative of the visual model. Other terrestrial applications use the learn model to find the next best viewpoints, but they're designed for terrestrial applications and not for spacecraft, so they often ignore orbital dynamics and fuel constraints. To the best of our knowledge, no methods have closed the loop between spacecraft guidance and learned shape reconstruction. And therefore, our contributions are threefold. We first close the loop by using our 3D shape reconstruction model to inform our guidance strategy to pick the next best orbit for a servicer to go to inspect our target. The second is we use our model training metrics to tell us when to switch orbits, as well as use parameter sensitivity metrics baked into our model to determine which orbit to switch to. And third, we have demonstrated this method in low Earth orbit simulations and have showcased 17% lower L1 loss and 56% lower delta V consumption than our simpler baseline approaches. Our strategy uses the pipeline split into a nav and guided section. In the nav section, we focus on shape reconstruction, where we orbit around a target spacecraft, collect images, and train our 3D shape model. If we detect that our training has saturated, in other words, we have learned enough from this orbit, we move into our guidance section. Using parameter sensitivities built into our 3D model, we score orbit candidates based on those sensitivity metrics. In other words, we look at the reconstruction utility of the images collected from that orbit, and we weigh that against the transfer cost it takes to get to that new orbit. If we transfer to the highest scoring orbit candidate, we then go and repeat the pipeline. A couple key assumptions that are worth noting on the navigation front. We're assuming that we have perfect pose knowledge of the spacecraft. The unknown uncooperative problem technically is unknown shape and unknown pose, but for the purposes of this research, we're just focusing on learning the shape of an unknown spacecraft. And we assume perfect knowledge of the relative pose. And we also assume we have perfect servicer attitude control, and that the camera always points towards the target, as you can see in this fly-through. We also assume ideal illumination, in that the sun is always behind the servicer and there are no shadows casted. As a result, we're getting these collected images that are made by a synthetic renderer that we use for training. Lastly, for our Canada orbits, we're using a predefined set of passively safe relative orbits rather than generating them live. One important thing to note is the evaluation metrics that we use both for training the 3D-GS model and also for grading our method. The first is L1 loss, which is a per pixel RGB comparison between your rendered image and your ground truth image. The second is SSIM, or Structural Similarity Index metric, where we look at local structures and textures in the reconstructed image and match those to the ground truth image. Our 3D shape model is the next major component of this pipeline, where we use 3D Gaussian splatting, or in other words, 3D-GS. In this, a scene is represented with the thousands of 3D Gaussian primitives, or 3D ellipsoids. Each Gaussian has a parameter vector, which stores where it is via mean, what shape it is via the covariance vector, what opacity it is via alpha, and what color it is via spherical harmonics. Collected images are then used to iteratively refine the 3D GS model by optimizing 3D GS loss, which is a combination of L1 and SSIM. And as a result, you can see here is an example of 3D GS training in action where we're trying to render a viewpoint from one image. Given our potential orbit candidates, we want to estimate how useful the images collected from that orbit is for improving the shape reconstruction. We can compute how sensitive a particular view is by taking the gradient of a rendered image, like you see here, with respect to that 3D GS parameter vector. In other words, we're looking at how the rendered image is going to change if the 3D GS model were to change slightly. So if you see here, we have a case of high sensitivity, where a small Gaussian perturbation has a large impact on the rendered image. On the contrary, we have a better refined model here, where the same Gaussian perturbation has a small impact on the rendered image. We can compute the per pixel sensitivity, as seen in this map, sum it across an image, and then for a given candidate orbit, we predict the viewpoints it will see, and we can compute what the average sensitivity scores will expect to see across all those images collected by that candidate. Then we get the feature score, which is the reconstruction utility of that candidate, and we'll use that to assess how useful the views from that candidate are. While training our 3D GS model from images collected on orbit, we keep a holdout set of images that are used for evaluation loss. When our evaluation loss is no longer improving, or in other words, the evaluation loss is not decreasing, in this case, you can see it's increasing, we decide to use our guidance strategy to tell us which orbit to switch to at the end of the orbit. Rather than using a fixed time window to determine when to switch, we're using our shape model to inform us on if the current orbit has provided all the useful information it can, and it's time to make that switch decision. For our orbit candidates, we're not optimizing over a continuous space of possible relative orbits. Instead, we define a finite set of passively safe candidate trajectories that are parameterized in terms of ROEs, or relative orbital elements. These candidates provide diverse viewing geometries around the target, and at each guidance decision, every candidate is evaluated using the J feature score and the delta V cost required to get there when using an impulsive maneuver. In our experiments, we consider three separate strategies. The first is our baseline, where we remain in a V-bar approach, or we're just separated by several meters away in the tangential direction. We do not actively move orbits, we just instead stay in the same orbit and observe the candidate from there. The second is a sequential strategy, where we sequentially move between orbit candidates in a globally optimal delta V order. This is considered to be the best case scenario, as we get the greatest viewpoint diversity by viewing all the candidates, albeit this comes with a high delta V cost as we take maneuvers at every step. The final is our guidance strategy, where we use our 3D GS model to selectively tell us when and where we should move candidates. We do take fewer, albeit more expensive maneuvers, but we're balancing the fuel cost with orbits that we expect to learn the most from. Through our simulations in low Earth orbit, we can showcase the use of parameter sensitivity as a metric for reconstruction utility. We demonstrate that as we iterate and train our 3D GS model, the parameter sensitivity decreases overall. We can also see that the quality of the shape estimate improves with more training. We consider two types of attitude cases. The first is where we use the target spacecraft, in which the target spacecraft attitude is fixed in the ECI frame. So from our perspective of the servicer's camera, the target is rotating. Inspecting visually, our baseline, sequential, and guidance strategies all provide comparable image quality. These images are rendered and compared purely for evaluation, and they're outside of the training set of images collected by the servicer in the pipeline. We can also look at this empirically by comparing the L1 and SSIM metrics as well as delta V. Our sequential strategy, which you can see in orange, provides modest reconstruction improvement despite visiting every candidate orbit and getting the greatest diversity. The proposed strategy maintains roughly the same reconstruction performance as the sequential strategy. However, it's able to do this while using 67% of the delta V. The baseline strategy, in which we don't move at all, it also has comparable image rendering quality, but it does this at no delta V cost. So active orbit switching provides limited benefit when the target rotation already supplies the viewpoint diversity. But let's look at another case. If we look at the attitude case where the target spacecraft is locked in attitude with the servicer, then if we remain in our V-bar baseline orbit, the views of the target are all identical. However, the baseline is providing poor quality visualizations, while the sequential and guidance strategy are able to provide decent reconstructions. As seen in the image metrics, once again, we can see our blue baseline is very poorly performing compared to the guidance and sequential strategy, where the sequential and guidance strategies can get up to 17% lower L1 loss. The guidance and sequential strategies are again comparable with respect to each other in terms of performance, but the guidance strategy outperforms the sequential strategy with 56% of the delta V cost. So when passive motion alone cannot provide sufficient viewpoint diversity, reconstruction-aware guidance substantially improves reconstruction while reducing maneuver cost. In conclusion, we've developed a closed-loop framework coupling 3D GS reconstruction and relative orbital guidance. We are determining both when and where to maneuver and doing this autonomously by using parameter sensitivity metrics and training evaluation metrics that are baked into our model. Our key findings show that the greatest benefit occurs when natural viewpoint diversity is limited. We can get 17% lower L1 loss at 56% of the delta V cost. In our future work, we plan to generate orbit candidates online rather than using a predefined library. We want to relax the idealized assumptions that we make about lighting and attitude control, and we also want to demonstrate this by using flight representative hardware. Thanks, and I'll take any questions.